Momentum's units, there's no fancy unit for momentum. You're multiplying mass times velocity, so the unit of momentum is kilograms times meters over seconds. There's no real creative unit for that. You're also going to see that it is Newton times seconds. When we get to impulse, you'll see that more directly. All right. Oh, talked about this already. So what would make an object very hard to turn, or what would make an object very hard to stop? Those two things that we just talked about, mass and velocity. The heavier something is, or the more massive that object is, the more difficult it's going to be to turn that object. And the faster it's going. So a bullet might have very high momentum because it's traveling very, very fast, even though it's got a low mass. Or a car just rolling down a hill would also have a lot of momentum because it's very massive, and even though it's got a small amount of velocity. Oops, clickers. I forgot about the clickers. We'll come back to this one. So what's the momentum of a 65 kilogram sprinter running east at 10 meters per second? 65 kilograms times 10 meters per second, so 650 kilograms times meters per second. Now it does have a direction. Momentum is directional. You can have momentum in the east or the west, or the positive or negative, unlike energy. Energy is always a positive value. It's a scalar. It does not have a direction. Momentum does have a direction, and that's because it has a velocity, and velocity has direction. Direction is going to be very, very important when we get to conservation, so keep that in mind. These answers for momentum could be negative, and that's perfectly acceptable. Calculate the momentum of a system. So this goes to that earlier equation we used. The momentum of a system is equal to the sums of all the momentums of the individual pieces. So you can look at the momentum of the whole thing or just an individual part of it. In this case, we're going to be looking at a system, or the whole thing. We have a 65 kilogram sprinter, represented by a ball, running east at 10 meters per second. We also have a 75 kilogram sprinter running north at 9.5 meters per second. So what is the momentum of the entire system? Well, we already calculated this guy. This guy's got a 650 kilogram meter per second momentum. What about this guy? 75 times 9.5. 712.5 kilogram meter per second system. Now our equation says that the total momentum of a system is equal to the sum of its individual parts. Can we add these two things together? No. Why not? Can we do the Pythagorean theorem on them? Momentum this way, momentum this way. In all honesty, you're not going to get this question on the AP exam. The important thing to know is that you cannot add them together because they're in different directions. Just as you can't simply add the velocity from the x direction to the velocity in the y direction to get total velocity. It's not how it works. You can't add things which are in different coordinate systems to each other. So Pythagorean theorem would be right. 650, 712.5. The resulting, for the total momentum, would be whatever that number is. We're not going to go through the math here. Some of you guys can do it on your own if you're so inclined. You're not going to get that question, but it's important to note that x and y are separate still. Anytime directions taken into account, the x and the y are different. Just like any other change, the change in momentum is the final momentum minus the initial momentum. So if an object's sitting on the ground and you go and push it, you apply a force, it's going to change the velocity and therefore change the momentum of the system. Or say you're in a car and your car is driving along the highway and you bail out. You jump out the door, what does that do to the system? Here's you in the car. Later on, here's you outside the car. What's changed? The system hasn't changed, but the momentum of the vehicle would have. What happened to the momentum of the vehicle after you jumped out? It might have changed because now it's less massive. We'll look at different examples of that, but one example is a kid sliding on a sled. Get two kids sliding on a sled, one kid falls off the back. Oops. Well, that guy gets to go a little bit faster because now he's got less mass that's dragging along with him. We'll look at that problem a little bit later. But don't forget, a change is always final minus initial. And that's going to come up as well later as well. So we're going to take a second and do a little lab here. Using only a meter stick, find the momentum change of a ball when it strikes the desk from exactly 1 meter. So why don't you guys get in groups of 2, and we will perform this little experiment.